Good evening, sir.
Good evening to all of you.
Good evening, sir.
Good evening, Bachai. Just let me open the notes. So in the last class, we discussed about the evidences in support of continental drift theory, I think so. We have completed the evidence or
We have
something
to
else?
discuss the fossil distribution.
Okay, so evidences from the fossils. So mainly the fossil study were performed in Gondwana block. It was found that evidences in support of continental drift theory, and in that we are going to study this evidences from the fossils. Evidences from the fossils. So from the Gondwana land, fossils of various plant as well as animal were recovered. This I'm just trying to make Antarctica. Here you will find this Madagascar. India. And Australia. So this is what representing Gondwana. And what was found that the fossils like Cynognathus, it was observed from northern part of South America as well as Africa. Fossils of Mesosaurus, they were recovered from southern part of South America as well as Africa. So here the Mesosaurus. Mesosaurus, it was also a reptile, 2 to 3 meter long reptile. Reptile fossils which were recovered from reptiles fossil recovered from southern part of North South America and Africa. And the fossils of Listosaurus were recovered from Africa, India, as well as Australia. So these were again the reptiles. Saurus, Listosaurus. And Listosaurus was also the reptile. So they are nothing but a reptile. Right? These are the reptiles. And their fossils were recovered from Gondwana. They are animal, and such a large distribution of animal can only be possible when the land masses were together. Such a large animal distribution. Animal distribution can only be possible when the continents were together. When the continents were together, then only we are going to have such a massive distribution of animal fossil. But you might say that animal can swim, animal can locomote. Although locomotion is also not ensuring such a massive distribution, but there may be a possibility that an animal can swim, so they can swim up to separated land masses by several thousand kilometers. But what if you are going to get a fossil which is plant in origin? It was found. So the fossils of Glossopteris, it was recovered from Africa, Madagascar, Antarctica, as well as it was also reported in India. So fossils of plant, that is Glossopteris. Glossopteris. It was reported from entire Gondwana. It was a primitive fern that is pteridophyte. Pteridophytes are seedless plants. They are seedless plant. That means they don't have seed even then. Their distribution was seen on entire Gondwana. Glossopteris. So for this means recovery of Glossopteris from entire Gondwana is telling the same story that continents were together somewhere in geological past. So the fossil, among the fossil, this Glossopteris is going to be the punch that is going to substantiate is somewhere in geological past, these land masses were together. And you can recognize the land masses like, what is it? Antarctica. Here it is Australia. This part is representing India. Here it is Africa. And this is South America. So remember this figure. And whenever you go for evidence from the fossils, just make this entire Gondwana. So study of Gondwana fossil is revealing the same story that somewhere in geological past, these continents were together. Is it okay? These continents were together. Because such a massive distribution of plant can only be possible when the land were together. If it is separated by 4,500 kilometers a water body, certainly plant is not going to be distributed. Is it fine? So this was the evidence from the fossil. What evidences we have covered? We covered evidences from glaciated landforms. Let me check. What are the evidences? Similarity of coastline we have covered. Fine. And similar rock strata, orogeny we discussed, coal deposit, forest cover. Then placer deposit we discussed, good. And then evidences from the fossils. It was discussed. Okay, fine. It was not totally discussed now. Fine. Evidence from glaciated landform as well as stellite deposit, paleomagnetism, and animal behavior. These are left over. Okay. So let me move on the next, and that is what? Similar fossils. And next is evidence from evidence from glaciated landform. Glaciated landforms. Glaciated landform and Tillite deposit. Tillite deposit. So when you talk about Wagner's research, so Alfred Wagner was actually engaged in the study of these paleoclimatic evidences. Paleoclimatic studies. And he found out that there was a Karoo glaciation that have taken place on entire Gondwana. At that very time, Gondwana was somewhere situated near the south. So this was the situation at that very time when Karoo glaciation was there, and the entire Pangaea was like this, Pangaea. And you know this southern part is what called as Gondwana. And this northern part is called as Laurasia. And when there was a glaciation, this entire southern part, which is what Gondwana, was actually under the glacier cover. Because glaciation can take place where in temperate region as well as polar region. It is also said that the South Pole, this is South Pole, which is still there. South Pole is nothing but the place where today's Durban is there. Now, try to see Durban in South Africa, Natal region. So where is the today's Durban? Okay, you will find Durban, South Africa. The South Africa was actually located near South Pole. This Africa, the southern tip of Africa, the Durban is located near South Pole. And due to this Karoo glaciation, you will find entire Gondwana is going to have glaciated landform. Glaciated landform. And you know, today this Gondwana get broken into, let's say, South America. This is South America. Equator here, it is Africa. And we have India also moved. And not only India, and have drifted towards north, towards equator, as per the understanding of continental drift theory. This is the present. Okay. So this is the present situation. Earlier, it was near South Pole. This is South Pole. And from here, the drift was like this. And this traces of this Karoo glaciation can be seen in South America. It can be seen in southern part of Africa as well as peninsular India. Do remember this is peninsular India. You will find this Karo glaciation, remnant of Karo glaciation as well as Australia. So this glaciation was recovered and the landform, glaciated landform plus tillite deposit. These were recovered from Gondwana. And glaciation cannot be possible in the tropical region. This is tropical region. Huh? This is tropical region. Now the continents have been moved to tropical region. But earlier it was not near the tropics. Earlier it was near the South Pole. That's why glaciation was possible on entire Gondwana. Glaciated landform means presence of glaciated landform or remnant of glaciated landform from entire Gondwana is telling the same story that somewhere in geological past these were together. These were together. The Gondwana were together. So you understand evidence from glaciation. Okay. Next one is evidence from magnetism. Evidence from magnetism. Evidence from magnetism. Suppose that there is a crust and this crust is what? Having certain volcanic eruption. This is the earth crust and there is a volcanic eruption and there is a lava flow that have taken place. This is the lava flow. So on the crust, because of volcanic eruption, this is the lava flow that have taken place. And this lava deposit have taken place on this earth crust. This is earth crust. Fine. And it was the first volcanic eruption that have taken place. And from here, this lava spread over there. And after some time, there is another lava flow that have taken place here only. Another lava flow. In some other geological period, this is another lava flow that have taken place. And lava is going to deposit. First thing you need to understand, inside this lava, this magma, when it was molten, certainly there will be ferromagnetic compound like iron, there will be magnesium, there will be nickel, there will be cobalt, and so on and so forth. So when it was in molten state, all these ferromagnetic compound get magnetized according to the polarity of its time, North Pole and South Pole. So you'll find that there is an alignment of ferromagnetic compound, and this alignment is what? According to the polarity. This is in case of layer L1. Another layer L2 is there. So in L2 also, there will be ferromagnetic compound and there will be some kind of alignment you will find over there. And this is what, according to the polarity present, and then it gets solidified. It becomes solid. So obviously when it becomes solid, that means it becomes lava. Then the alignment cannot be changed. Okay. According to the magnetic line of force, all the ferromagnetic compound get aligned as per the polarity. And similarly, suppose that there is another lava flow that have taken place. And in this lava flow also, there will be some polarity. And there is a magnetization. Let's say this is layer L3. There is another lava flow in some geological period just above this earlier lava flow. So it may be possible there are many such volcanic eruptions that have taken place time to time, and all these volcanic eruptions get magnetized as per the polarity of its time. It can be possible. Yes or no? Yes. Fine. So in this also there will be some kind of magnetization. There is also a kind of magnetization, and here also the ferromagnetic compound get magnetized along with the pole. So all these 6 layers of lava must show same polarity. But what was found that in these layers, this is what lava flow, the polarity was different. Polarity was different. That means the alignment of ferromagnetic compound in each layer was not same. It is going to be different. It can only be possible when this crust, that is what the continent, is moving from one place to other place. For example, suppose that this is North Pole and here it is South Pole, and somewhere in geological past, India was here. And there is some lava flow that have taken place on the Indian landmass. So obviously, it will be according to the polarity of this time. Now India reached over here. And there is another lava flow. So this lava flow is of just above the previous one, isn't it? And you get another type of polarity. Okay. And further you find that India moved over here. This is the present scenario. And due to this, what happened? Another lava flow in which you will find difference in the polarity. So this difference in the polarity is because of India drifted. It is not because of pole is going to change. So difference in the polarity in different lava flow is telling the story that continents were drifted. You are not going to change the pole immediately, na? But there is a change in polarity which is reflected in different lava flow. This is L1, here it is L2, here it is L3, and in all lava flow, the alignment of ferromagnetic compound was different. And it is telling the same story that, okay, it is not the pole which is going to be changed, rather the continents were drifted, and earlier it was near South Pole. Now it is north to equator. North to equator. So this is what supporting the continental drift theory. Evidence from magnetism also supporting the continental drift theory. Is it okay to everyone?
Yes,
Understood?
sir.
Okay.
Yes, sir.
Karoo glaciation, it was somewhere in uh, means 300 million years from today. This is the time of Karoo glaciation. Karoo glaciation was at the time of when this Pangea was intact. So somewhere 300 million years from today, when the entire landmass were together. This was the timing of Karoo glaciation. And after that, Tethys Sea was formed, and then Gondwana and Laurasia broken further and drifted apart. Is it fine? Next is evidence from animal behavior. Animal behavior. Evidence from animal behavior. So basically this was indirect evidence and it was studied. The lemmings were studied. Lemmings. They are rodents. Rodents. They are found in Scandinavian country. Scandinavian Peninsula, and their behavior was studied. It was found that, especially on the advent of winter season, in winters, these lemmings start migrating towards west. Lemmings start migrating towards west and jump from west coast into the Atlantic Ocean. And jump from west coast into the Atlantic Ocean and commit mass suicide. Mass suicide. So this animal behavior was seen like a mass suicide. And what was the condition thought to be? Like, this is a Scandinavian country, Norway, you know Norway. Here it is the Europe. This is Mediterranean. So they start migrating towards west. And they jump from the Norway coast in Atlantic Ocean. Especially in winter season. And their mass suicide, in lakhs in number, their mass suicide were reported from here. It was thought that the lemmings are so, they are showing austerity, and for their young ones, they leave their young one and they migrate towards west, and they died over there so that they survive the scarcity of food, especially in winter season. Because on the advent of winter, they have abundance of population. So before winter, there was a lot of grasses. So their population is what? Abundant population. But when there is a winter is approaching, they start migrating towards west, and they jump from the cliff of Norway into the Atlantic Ocean, and they commit mass suicide. When it was first studied or seen, it was thought to be the lemmings are very, what you can say, social animal. The elder or the older one migrating towards west, and they go for mass suicide so that their young ones survive, even in case of scarcity of food. But it was thought that why they are going to cover this 600 kilometer to jump over there? Why not they just cover few 10 to 100 kilometer and jump over here and commit the mass suicide? That means they are moving towards west, and not because they want to do suicide, but because of something else. So the animal behavior develops through millions of generations. It's a behavior which is developed through generation. So it was concluded that lemmings were fond of migrating towards west in search of food and space. So they are in search of food and space. Fine. And earlier, North America as well as Europe, they were close to each other. Atlantic Ocean was not there. So these land masses were close to each other. At that very time, this was the scenario. Maybe possible. The Atlantic Ocean is not so big. So Lemmings, earlier, these land masses were together. Maybe Atlantic Ocean was not so big. So they are migrating towards west. They reach to the new land. But what happened? This Atlantic Ocean is spread over there, and both the continents were moved apart. Then they jump over there, they migrated towards west, they swim, but they get perished because they are lemmings. So they are not able to swim the huge Atlantic Ocean. So initially, the animal behavior was considered as they are going for mass suicide for their young one. But later on, it was concluded that this westward movement is just in search of food as well as space. But in the pursuit of this very project, they perished in crossing the Atlantic Ocean, which is what? A huge water body. And this animal behavior is also supporting somewhere in geological past, these land masses were together. These land masses were together. Is it understandable? Lemmings behavior is understandable or not?
Yes, sir.
Okay. Everyone is syncing with this. So all these information is supporting that continents were drifted. But there are certain demerits. We talked about demerits of this continental drift theory or not?
Yes, sir.
We talked about
Yes,
demerit.
sir.
Okay, fine. So these are the evidence which was supporting that continents were drifted. But this continental drift theory simultaneously was not able to explain the mechanism of this kind of drift. That's why the theory was discarded, but it acts as a bridge theory. Bridge theory. And it opened a new horizon of research. New horizon of research that led us to plate tectonics. Plate tectonics. It was for sure that continents are drifting apart, but the force is not sufficient enough to drift the continent. That's why, what are the things which has to be discovered? Number one, force. Number two, study of earth crust. So on the earth crust, we happen to have continent, which can be seen, continents. But what is going on inside the ocean is known. So first thing, to discover the force as well as to discover the ocean flow. These were the things which were required. And it was thought, let's talk about ocean floor also, because we are not knowing what exactly is going on inside the ocean. That's why from in post-drift study, the first thing was performed, and it was post-drift study. The period is from 1912 to 1966. This is the period of post-drift study. And in this phase, the first thing was performed was sea floor mapping. Sea floor mapping. It was done. Okay. Sea floor mapping was done. And then other things are done. I'm just going to make you understand what is the post-drift study, what were the study that were made in this phase, and how we are able to reach up to plate tectonics. So seafloor mapping was done in order to know the behavior of ocean floor, because at that very time it was known that continental floor is floating over oceanic floor, Sial floating over seamount. And seafloor mapping was done by using a technology which is called as sonar bathymetry. Sonar bathymetry. And in sonar bathymetry, ultrasonic wave was used in instrument that is sonar, sound navigation and ranging, and sea floor was mapped. Suppose that this is ocean and there will be different, what you can say, parts in the ocean, and almost for all 10 years, entire world was engaged. Means all those concerned to the geography, geology, oceanography, they all are doing one job, and that was ocean floor mapping. They put this sonar, they sail their boat in the boat, and by using this sonar bathymetry, they send this ultrasonic wave and they measure the ocean floor. And ocean floor map was created. Map was created. And very peculiar topographical feature were observed under the water. So let me explain those feature. So when you see the ocean, you will find following topographical feature. Like when you are moving towards the high sea, you will find there is a zone where the depth is what? Gradually increasing. Then there is a zone where the depth is rapidly increasing. Then there is a monotonous region, and this we call continental shelf. Then we have continental slope and deep sea plain. So up to here, this is the point that is called as shelf break. And then beyond it, here it is continental slope, and this part is called as continental shelf. Continental shelf up to the depth of 180 meter. This is what we call continental shelf. Continental shelf. This part is continental shelf. And you will find that the depth is gradually increasing. The depth is gradually increasing. But beyond this shelf break, you will find that the depth is rapidly increasing. Fine. Here, the slope is very gentle. Slope is very gentle. Of the order 1 to 2 degree. This is the gradient. While in continental slope, slope is steeper. Steep. It is more than 5 degree. Average depth of continental shelf is up to 180 meter. 180 meter is the average depth, while the continental slope has average depth reaching to 2000 meter to 3000 meter. Continental shelf and continental slope both are the part of continental plate. Continental plate. In case of such plate where the ocean floor as well as continental floor both are same, कहने का मतलब है कि जहां ओशन और कॉन्टिनेंटल फ्लोर दोनों एक हो, like this. So ocean floor, which is made up of basalt, and continent is made up of what you can say granite and all that. So here it is ocean. This is ocean floor, ocean crust, and this deep ocean crust is called as deep sea plain. Deep sea plain, and deep sea plain is extensive. Average depth is 3,000 meter to 5,000 meter. This is deep sea plain. But in case of such continent where the ocean and continent is what? On same plate. This is continent. And then in this case, we happen to find a peculiar topography at the joint of oceanic and continental crust, and this is called as continental rise. When you are coming from the deep sea plain, you start rising up to the continent. This joint is called as continental rise. Continental rise. Fine. So continental rise always present when the ocean floor and continental floor is going to be same. For example, if we talk about North America plate and Atlantic floor, South America plate and Atlantic floor, or African plate and Atlantic floor, as well as Indian Ocean floor, there you will find this continental rise. Fine. So continental shelf, continental slope, continental rise, and deep sea plain. These are the peculiar feature of ocean topography. Almost 8.6% of total area of ocean belongs to continental shelf, and almost 8.5% area is continental slope. And the deep sea plain accounts for almost 80% area of the ocean. 80% area of the ocean is what? Deep sea plain. It is also called as abyssal. Abyssal plain. Abyssal plain or deep sea plain. Okay. Deep sea plain or abyssal plain. Is it fine? Hello?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Few more landforms were means topographical feature were seen, and the next one is mid-oceanic ridge. Mid-oceanic ridge. It was observed in case of Atlantic Ocean that inside the mid of ocean there is a continuous effusion of magma taking place, and this magma get solidified within the water and creates this mid-oceanic ridge over here. So this magma that comes up and gets solidified, comes up and gets solidified within the water, and that is what we call mid-oceanic ridge. Mid-oceanic ridge. There is a continuous effusion of magma taking place. Continuous effusion of magma taking place, and it spread in form of new sea floor like this. A new sea floor is continuously created over there, and this we call mid-oceanic ridge. Mid-oceanic ridge. And as you move from the center of this mid-oceanic ridge, हाँ कुछ कह रहे हैं आप? Hello.
No, sir, nothing.
So I'm talking about mid-oceanic ridge. So it is present in the mid of the ocean. And later you know that there is a divergence taking place and magma comes out from the interior of the earth. And there is a continuous effusion of magma. And this magma gets solidified and new ocean crust, new ocean floor was being made, is under construction. It was found that when you are at the center of this mid-oceanic ridge, this is the point. You'll find new magma, means today's magma you are going to. But as you move away from the center in both the direction, you will find age of the rock is what? The rock is increasing. That means where you are going to get new rock at the center. But as you move away, the rocks are becoming older and older. It was found. Where this mid-oceanic ridge first studied in Atlantic Ocean. Atlantic Ocean, mid-oceanic ridge. Then this mid-oceanic ridge was also reported in Indian Ocean. Indian Ocean, mid-oceanic ridge. And then in East, basically Southeast Pacific Ocean. Southeast Pacific Ocean. This mid-oceanic ridge was also reported over here. So presence of mid-oceanic ridge give a clue that ocean floor formation takes place continuously. Ocean floor formation is taking place continuously. This is the clue from mid-oceanic ridge. And not only this, the another topographical feature which was also giving some clue was trenches. No? So trenches were observed. Trenches are the deepest. These are the deepest part of the ocean. Deepest part of ocean. And they are even 3,000 to 5,000 meter deeper from the deep sea plane. So deep sea plane is already deeper. And something which is even deeper from deep sea plane with a range of 3,000 to 5,000 meter, then they are called as trenches. Either this much deep or it is present near the subduction zone. Subduction zone. What is subduction zone? Let me explain. Suppose that there is a continental plate. There is a continental plate. So this is continental plate like this. And we happen to have this continental plate. Okay. And obviously there will be continental slope, continental shelf. This first there will be shelf, then there will be slope. And obviously there will be ocean floor too. Ocean floor. So this is the plate, which is what? Oceanic plate. But here it subducts below the continent. So there is a subduction zone. So you'll find subduction zone over here. Let me show you this. Let me make it even deeper so that you can connect it. This is the continent. This is the continent. And here, this is the ocean. Ocean floor with subducts below the continent. Because ocean floor is made up of, you all have this idea, it is made up of silica, magnesium, and it is made up of silica, aluminium. This is continent, and here it is ocean floor. So this is what ocean floor. Here it is the deep sea plain, and this point is called as trench. So where we happen to see the trench near subduction zone. And near subduction zone, oceanic crust is actually subducted below the continental crust, and there is a continuous melting of this crust taking place because the temperature is too high inside and it is getting melted, and formation of magma takes place over here. Magma. Although these were not seen through bathymetry, but what was found that the trenches are somewhere where the movement of plate is taking place downward. So here destruction of plate is taking place. Destruction of plate. Destruction of oceanic plate is taking place. So by sonar bathymetry, it was not concluded that destruction of oceanic plate is taking place. But do remember, near subduction zone, oceanic plate is going to be consumed. Fine. These are the trenches, and there are many examples of trenches, like we have Mariana Trench, Mariana Trench, we have Filipino Trench or Mindanao Trench, Mindanao Trench, we have Kurile Trench, Peruvian Trench. These are the deepest trenches, and there are many more, but to remember, these are the trenches. So what was found? First one is mid-oceanic ridge, another one was trenches. And then what was done after knowing this ocean floor? Estimation of age of the rock was done. Estimation of age of the rock. So rocks were, their age were known by using uranium, radioactive uranium dating. And what was found that continental crust has the oldest rock with an age of 3.2 billion years. 3.2 billion years. This is the age. Continental crust has the oldest rock with age 3.2 billion years, while oceanic crust has the oldest rock, and that is just of 200 million years. That means Prima facie, you will find that continents were made earlier and ocean were created just 200 million years. But this is not true because first life was originated in the ocean. That means ocean crust was there. What is your inference? Then you start thinking smartly that ocean crust is dynamic, is dynamic. That's why in last 200 million year, all the ocean get consumed and new ocean was formed. Ocean crust is dynamic, and this dynamism was substantiated by mid-oceanic ridge, near mid-oceanic ridge, near mid-oceanic ridge, new ocean crust is being formed. Is being formed. New ocean crust is being formed. That's why you will find the age of the rock near the center of the mid-oceanic ridge is new. While you are moving away from it, you will find the age is what? Increasing. This is what mid-oceanic ridge. As you move away, you will find old age rock. Here you will find new rock. So it was clear that near mid-oceanic ridge, there is formation of ocean crust, and for certain, somewhere it is getting consumed. Somewhere ocean floor get consumed, and then the trenches were studied further, trenches, and it was found that near the trench there is a subduction taking place, subduction, and slow movement of plate was observed. Okay, and then it was concluded that ocean crust is dynamic. Somewhere it is getting formed and somewhere it is getting consumed. On the expense of older ocean floor, new ocean floor are being constructed. So this was the finding of ocean floor mapping. And what was the further discoveries? Further discovery was regarding force. So let's find out some theory related with forces. So to understand the forces which is going to cause the crustal movement has to be studied. And the first theory was convectional current theory. It was proposed by Sir Arthur Holmes. In the year 1928. In order to understand the endogenic forces, the endogenic forces are responsible for crustal movement. So in convectional current theory, Arthur Holmes concluded that inside the earth crust, inside the earth temperature is very high. Temperature is very high, very high. And there is a continuous rise of convectional current takes place. There is continuous rise of convectional current taking place. So this is the crust. Fine. And it is moving because of very high temperature somewhere inside the earth, very high temperature somewhere in the mantle. And from here, there is a continuous rise of strong convectional current. Strong convectional current. And you can see there are three distinct arms of these convectional current. One that is ascending arm, ascending arm. This one is transverse arm, and here it is descending arm. Descending arm. These convectional currents are originating from the mantle where there is very high temperature. Very high temperature. And these strong convectional current are responsible for lifting the magma up. It lifts the magma up. Magma comes up and spread over in form of mid-oceanic ridge. Spread over in form of mid-oceanic ridge. And the continuous transverse arm is pushing the crust apart and causing the crustal movement. And that's why this crust is moving like this under the influence of convectional current. So this is what a figure of convectional current theory. Fine. So inside the earth, there is very high temperature from where the convectional currents are formed. They are very strong convectional current. They are very strong and they have peculiar arms also. Number one, there is ascending arm. It rise the magma up, take the magma up. There is transverse arm that drags the crust apart. This is the crust. At this very time, the plate was not given. The term plate was not given. That's why it dragged the crust apart. And the descending arm further pushes the magma up. This is the cycle that takes place inside the earth interior. And this cycle is responsible for crustal movement. And the cycle is taking place in mantle. And there is asthenosphere. Upper part of mantle is called as asthenosphere. So you will find this convectional currents are rising in the mantle. And these convectional current are responsible for crustal movement. This is what convectional current theory. Why the temperature inside the earth is high? This is a question. Why there is high temperature? There is high temperature. So it is due to four reasons. Number one, residual heat. Residual heat, which is present at the time of formation of earth. This heat is still there. The second is presence of radioactive elements. Abundance of radioactive elements. And from there, the continuous heating takes place. Third, exothermic reaction. Exothermic reaction. So you know rocks are made up of mineral, and mineral can perform this exothermic reaction. Heat is released. And the fourth thing is friction between the core, between the solid core and churning liquid outer core. Churning liquid outer core. So outer core is moving. Both are made up of what? Both are made up of nickel and iron. So this is outer core. This is outer core. And here we have inner core also. Inner core is solid. This is solid. And outer core is liquid. And due to rotation of Earth, outer core is continuously moving. And due to movement near the interface, try to see the interface. This is the interface where continuous friction is there. So this is also made up of Nephe. And here it is also made up of Nephe. So you'll find there is a friction, Nephe, between the core and outer core. And due to this massive friction, energy, the heat is coming from here, and there is heating effect. Continuously heat comes out from here. And this heat is what? Responsible for heating effect. So why there is churning of outer core? You know, because of rotation of Earth. So friction between the solid core and churning liquid outer core is also responsible for release of heat. Release of heat. And this heat is responsible for what? Rise of convectional current or heating of interior of Earth. And this convectional current is so strong that it can move the crust up. So earlier we were discussing that is there any outside force responsible for crustal movement? But what was found that it is the endogenic force, strong convectional current, which is responsible for crustal movement. This is what convectional current theory talks about. Another theory which support endogenic force is called as ridge-push theory. Ridge-push theory. And in ridge-push theory, you can easily understand that when there is a movement of how this movement of crust is taking place. Suppose that these are the two crusts, and here we have the mid-oceanic ridge. Magma flow takes place, and there is formation of mid-oceanic ridge. Mid-oceanic ridge is being formed. Then what happened? This magma gets solidified. This magma get solidified. But what happened? Further magma pushed up. And due to this new magma, these crusts are moving apart. So there is a push in both the direction exerted by this ridge. So when magma comes out, it gets solidified. Further magma is pushing this ridge apart and hence causing the movement of the crust. So this crust is also drifting apart, this crust. So this is what we call ridge push theory. So ridge push is also pushing the crust in the same direction. Try to see collectively, there is convectional current. Here it is convectional current. Along with it, there is a ridge push also. So the crust is moving apart like this. Is it fine? And the next one is slab pull theory. Slab pull theory. Let me explain a little bit more slab pull theory. In order to understand slab pull, we need to understand isostasy first. Okay. To understand slab pull theory, I would like to tell you something about isostasy. So isostasy is an equilibrium. You know, this is the lithosphere, lithosphere, and this lithosphere is floating over what? This lithosphere is floating over asthenosphere. So this is asthenosphere. We have seen it in the interior of Earth. So this lithosphere is floating over asthenosphere. And not only this, lithosphere is containing various loftiest of all type of mountain like Mount Everest and all, which is reaching up to several kilometers, let's say 8,850 meter height. This is the maximum height. But any time this mountain is not going to fall. That means there is a clear-cut equilibrium between lithosphere and asthenosphere. And this equilibrium is called as isostasy. Isostasy is a kind of equilibrium between lithosphere and asthenosphere. And this, as long as this equilibrium is there, lithosphere floats over asthenosphere. So this is what isostasy. But when this equilibrium is going to be breached, then what happens? Asthenosphere is not going to balance the lithosphere weight, and asthenosphere leave that weight on its own. So in that case, this slab itself start getting pulled by the gravity. Here the entire weight of the slab, weight the slab is actually balanced. But what happened when this isostasy get breached, then asthenosphere is not at all bearing the weight of that subducted part. And it happened when there is subduction that takes place. Suppose that this is the plate that gets subducted. Obviously, it gets subducted below continental plate. This is continent. Fine. This is continent. Here it is ocean. So this is ocean. And this is continent. And here it is ocean. Oceanic crust. अभी प्लेट नहीं कह सकते इसे क्योंकि इट्स अ टाइम ऑफ 1940 कॉन्टिनेंटल crust. Oceanic crust is denser, hence it subduct below the continental crust near the trenches. This was known. It is less denser. Why? I have discussed already. Now what happened? It is actually floating over asthenosphere. As long as it was just floating over asthenosphere, there was no problem. and the entire weight of the crust is actually balanced by asthenosphere. This is asthenosphere. But when this plate subduct into the asthenosphere, what happened? This isostacy get breached. And first thing, this plate is going to melt. Because in asthenosphere, near this zone, temperature is of the range 1000 degrees centigrade. And this is what we call Benioff zone. Here the melting of plate takes place. Not only this much plate, which was earlier balanced from here to here, this much plate is having certain weight, isn't it? And this weight, let's say mg, start getting pulled by the Earth's gravity. अब Earth इसे खींचना शुरू करेगी. So there is unbalanced force. So obviously this will be pulled like this. So if this is the direction of pull, this entire crust start moving like this. Okay. And this is called as slab pull. So this slab, which is subducted slab create unbalanced force, and due to isostatic disequilibrium, this unbalanced force start pulling entire slab towards subduction zone. Subduction zone. This is what we call slab pull theory. So slab pull is also pulling the crust in the same direction. Try to see. This is what slab pull. Ridge push, slab pull, and convectional current. These three are taking the slab apart. So this is what unbalanced force. This much slab is subducted. So here it is mg, which is taking it towards the Earth's center of the Earth. And that's why the entire slab is going to have a tension. And this is dragging the slab towards the subduction zone. So all these three forces and three theories were able to explain the extent of endogenic force. So the crustal movement is attributed to endogenic force. Endogenic force that include number one, convectional current, strong convectional current. Number two, massive ridge push. And number three, slab pull. So all these three forces were responsible for crustal movement. These were discovered by 1940. In 40s, these were discovered. And ocean floor map also done. Then by 1961, Harry Hess will come. Harry Hess will come with his theory, sea floor spreading theory. Sea floor spreading theory. on the very basis of various studies conducted by Harry Hess on mid-oceanic ridge of Atlantic Ocean, Harry has propounded this seafloor spreading theory. Fine. According to this theory, ocean floor is dynamic. Ocean floor is dynamic. Somewhere it is getting consumed. Somewhere it is getting consumed. And where is the zone? Near the trenches. And somewhere it is getting reformed. Reformed. Somewhere it is getting consumed and somewhere it is getting reformed. And not only this, net area of the Earth's surface remain constant. Remain constant. Net area of the Earth's surface remain constant. Okay. Seafloor acts as conveyor belt. Why he named it seafloor spreading? Because somewhere it is getting consumed and somewhere it is getting reformed. So actually seafloor spreading takes place near mid-oceanic ridge. And due to seafloor spreading, continents are drifted apart. Fine. So how the continents are drifted apart? Because of seafloor spreading. Let's take up the example of Africa, India, as well as Eurasia. So here, this is the Gondwana land. And north to Gondwana, there is Tethys Sea. This is the Tethys Sea. And this Tethys Sea was subducting below another continent, that is what? Eurasia. This is Eurasia. Fine. This is Eurasia. Here it is Gondwana. And this water is of Tethys Sea. This is Tethys Sea. Now what happens? Somewhere below the Gondwana, there is a rise of convectional current that takes place. And due to this Gondwana was broken. From here, Gondwana was broken. And because of convectional current, Gondwana start moving like this. There is divergence that takes place. And because of this movement, Tethys sea floor start moving in this direction. And there was subduction. And due to subduction, this was the unbalanced force. And it start pulling the slab towards this side. Now what happened? Gondwana broken into Africa, India, and Australia. Let me show you that. So I'm just showing you Africa. This is Africa. Fine. This is Africa. Is it okay? Here it is India. North to India. Let me show you one more figure it will take. Okay. Let me draw one more figure. This is Africa. And here it is India. So this split was there. And not only split, what happened to the Tethys? This is the plate of Tethys, which is subducting below Eurasia. This is Eurasia. Fine. So this is Eurasia. Here it is the Tethys Sea. This is India. This is Africa. And you know this movement is like this. Here the divergence takes place. And what happened to this Tethys plate? It get melted and there is formation of magma. And this magma has to be readjusted. That's why it is transferred over here. And this magma comes out. This magma comes out over here. And the new sea was new sea floor start taking shape, right? And slowly and gradually, again, there is rise of convectional current like this, taking the magma up. There is a ridge push, slab pull, and then what happened? Now you can see that Africa is here, India is here, and this is what the Tethys Sea, which is here, and what is it? Eurasia. And there is a narrow Tethys Sea left over, but there is formation of a new ocean. New ocean was formed between India and Africa, and there is formation of mid-oceanic ridge. There is formation of mid-oceanic ridge over here. This is the mid-oceanic ridge of Indian Ocean. Now the sea floor spreading takes place in Indian Ocean. Indian Ocean getting formed. And the sea floor spreading takes place here. And due to sea floor spreading of Indian Ocean, the Tethys Sea day by day get consumed. Here it is Eurasia. This is India. And this is Africa. And ultimately what happened? India and Eurasia collided with each other and there was formation of Himalaya because of buckling up of the sediment as well as continent. So Himalaya was formed from the Tethys Sea. Still the Tethys is present. A remnant of Tethys Sea is present north to the Africa. But where is the sea floor spreading taking place? In case of Indian Ocean. So Indian Ocean was means newly formed, it gets stretched, and due to formation of new sea floor spreading, the India and Africa moved apart. Fine. And this was the theory which revolutionized the theory and it solved many, what you can say, problem. And that is what we call sea floor spreading theory. Is it understandable to everyone?
Yes, sir.
Yes, sir.
Fine. So
Yes,
sea
sir.
floor spreading, yes. Any query from your side?
No, sir.
Okay. Is it understandable to everyone? Fine. So everyone is not joining the class. Today we are just 8 now.
Yes, sir. और एक चला गया।
एक और चला गया। क्या बहुत कठिन लग रहा है क्या आज का टॉपिक?
नो सर।
No, sir.
These are very important topic. Every year you will find some question in, even in GS it is going to help you. Okay, so this is what seafloor spreading theory. So in seafloor spreading theory, you will find that the net area of the earth crust remain constant. Seafloor spreading takes place, new ocean floor is reformed, and near subduction zone, there is a consumption of seafloor. Basically, the name of this theory must be seafloor consumption and seafloor spreading theory. But seafloor spreading is going to cause the drift in the continent. That's why it has been taken as a, what you can say, heading of this theory. Harold has proposed this theory. Okay, seafloor spreading theory. So this was the case up to 1961. And then what happened after that? In 1963, another theory will come, and that is what hotspot theory. It was given by James Tuzo Wilson. The same person in 1965 will give you the concept of plate, and in 1967, Mackenzie Morgan, and Parker, on the very basis of the above theories, which has been given in post-drift study, they propounded neo-global tectonics. Neo-global tectonics. It was nothing but extension of seafloor spreading theory on the very basis of concept of plate. You all have this idea hotspot theory by J.T. Wilson. In the interior of Earth, we have discussed it. याद है ना?
यस सर।
Interior of the Earth topic.
यस सर।
Fine. And the concept of plate is given by same person, J.T. Wilson. And you know this plate is made up of layer. It's a lithosphere, which is made up of Sial. It is made up of Sima, and it is also including the upper part of upper mantle. So this three, Sial, Sima, and upper part of mantle, this constitute lithosphere. In the interior of Earth, we discussed it, lithosphere, and this lithosphere is divided into different units, and these units are called as plates. So it may be oceanic plate, that means largely it is made up of Sima, that's why it is denser, and it may be continental plate, largely it is made up of Sial, and hence it is less denser. The density of Sima is reaching up to 3 gram per cc, and density of Sial is 2.7 gram per cc. Okay. And the decision of oceanic plate and continental plate is first on the basis of area and second on the basis of composition. Okay. Composition as well as area both considered. Primarily it is the area, but yes, sometime the composition, and if it is going to be of what? Silica and magnesium, certainly it is going to be oceanic plate. Fine. So this is what lithosphere and the concept of plate, which is already the part of our interior of Earth. So on the very basis of these two concepts and along with this sea-floor spreading theory of Harry Hess, this plate tectonics was given. Initially, it was independently given as neo-global tectonics, and later it became plate tectonics. Later it became plate tectonic theory. So tomorrow we will learn about this plate tectonic theory in length and breadth. So today I'm going to stop the class here. So tomorrow we will go for plate tectonic theory. So once you read the post-drift study and make a notes out of it, almost within in 600 words, so that you are capable enough to write any of this topic in 200 words, always. So you must prepare a notes like what is concept of plate, what is hotspot theory, 200 words, what is seafloor spreading, 200 words, isn't it? And not only this, uh, you must prepare notes on convectional current theory, ridge push theory, slab pull theory, at least 200 words on each. Fine. So read it again and make notes out of it and try to solve the question in PYQs that has been given. So now you start writing answer because now we have reached some considerable point and we have covered some part of geomorphology. So you start writing some answers. Fine. Like continental drift theory is over, plate tectonics is going to come tomorrow. It will be tomorrow and the day after tomorrow, we will cover the plate tectonics also. So this is how evidences we have covered. Fine. So please go through it and mark this very important. Now evidences from the fossils. So you just prepare a notes. I already
Sir,
gave notes. Fine. Even then, you must be prepared with the topics in a length as well as
sir,
yes.
sir, what is your Wilson cycle?
Wilson cycle. Basically, Wilson cycle is what? Formation of Pangea and then reformation of Pangea 2. So basically it is, I'm just giving you the Wilson cycle, idea of Wilson cycle. It was also proposed by same J.T. Wilson. He said, J.T. Wilson said, I will discuss it after the plate tectonics. This Wilson cycle is talking about that there was a Pangea 1. This was Pangea 1 somewhere 700 million years ago. And it was surrounded by Panthalsa. And due to endogenic force, this Pangea 1 was broken into different land masses and they drifted apart. And after 400 million years, they again joined to form Pangea 2. Pangea 2. And this Pangea 2 again broken in form of Angara land and Gondwana land. And the new sea floor is being formed. The old sea is getting consumed. And it is also taking a shape of North America, South America, then Eurasia, then Africa, Australia. And one day what happened, this North America moved like this and entire Pacific Ocean is going to be vanished. Eurasia, North America, Africa, South America, Australia again come together and there will be formation of Pangea 3. Again it will be broken and drift will be there. There will be new ocean formation takes place and this process of drifting of land will go on, which is what called as Wilson cycle. Is it understandable? Wilson cycle. So the story started from somewhere 700 million years ago, and then Pangea 2 was formed, continental rift theory we have seen. Now we are in the second season of Pangea, isn't it? And what happened after millions of years from today, these Pangea 3 formation takes place, like you can see that North America and South America is what? Moving towards west, and the Pacific Ocean in between them. Here it is Eurasia, here it is Australia, is getting consumed. So one day this Pacific Ocean getting consumed, and what happened? Eurasia and Africa is also what? Moving towards east, and they will come together, and there will be formation of another Pangea. Is it fine? So this land masses are drifting apart on the expense of ocean floor. Somewhere ocean floor is getting formed, somewhere ocean floor is getting consumed. And that's why there is formation of this kind of cycle, which we call Wilson cycle. So Wilson cycle will be understood in length and breadth when we discuss the plate tectonics, and we put together the plate tectonics as well as what you can say formation of Ural Mountain, Appalachian Mountain, formation of Aravalli, isn't it? Together, then you understand it's not a final plate tectonics, which is right now. Since time immortal, it is going on. This is what we call Wilson cycle. Is it okay to everyone?
Yes, sir.
Okay. So shall I stop here?
Yes, sir.
Fine. So tomorrow we'll meet and then we will decide the new topic. We'll discuss the new topic. Thank you very much.